Section 6.3, Systems of Linear Equations in 3 Variables. Here's an example of a system of linear equations in 3 variables. So we have this top linear equation in 3 variables, this second one, and this third one. A solution to this system can be written as the ordered triple 3, 2, 1. Or typically we would just get back something in the form x, y, z. Let's check if 3, 2, 1 is actually a solution to this system. So again, it's in the form x, y, z, so we're saying that x equals 3, y equals 2, and z equals 1. And if this is a solution to the system, then when I substitute x, y, and z into each of these equations, it should give me back true statements. So I'll start with the top one. So 2 times x, which is 3, minus 3 times y, which is 2, plus 4 times z, which is 1. I want to know if this is equal to 4. That's 6 minus 6 plus 4. And yes, it does give me back 4 equals 4. Try to plug in these substitutions for your variables into the next 2 equations and see if you also get back true statements. And then come back and check your work. And you should have gotten that all of them give back true statements. Since we get back a true statement when I make the substitution into each equation, we can say that 3, 2, 1 is a solution to the system. Solving a system of linear equations in 3 variables. Step 1, eliminate one variable, such as x, from 2 of the equations. Step 2, apply the techniques from section 1 to solve the remaining system, because once you eliminate one of the variables, you'll be left with a system of only 2 variables, which is what we learned how to solve in section 1. So that means you can use the graphing method, the substitution method, or the elimination method. Now, if there are no solutions for the 2 remaining variables, so you solve the system you have left and you get back no solution, then you have that the system of 3 equations also has no solution. If there are infinitely many solutions for the remaining 2 variables, let's assume that you eliminated x, so you're left with y and z, and when you solve that system in 2 variables, you get back infinitely many solutions. Then what you do is you write y in terms of z and proceed to step 3. Step 3 says substitute the values for y and z into one of the given equations and find x. The solution is written as an ordered triple, x, y, z. And if possible, so if you get back actual nice numbers, you should check your answers. Exercise 1. Solve the system. Just a word of warning, these problems where you're solving systems that are even bigger now can get pretty messy. So do your best to try to be somewhat organized. Sometimes I even label my equations, label equation 1, equation 2, equation 3, and then I write myself notes about what I'm doing to those equations as I do my work. That way, in case I make a mistake, I can go back and I can see what I was trying to do. Also, these might take quite a bit of time, and it is a good idea to check your work because sometimes you'll do the entire problem and then you check your work and something was wrong and it doesn't actually work. So try not to get frustrated if these end up taking you a long time. Believe me, they take me a long time too. Let's look at problem 1 together. The first thing we want to do according to our steps is we want to eliminate one of our variables. And you can choose to eliminate whichever variable you want. I think just looking at the way this is set up, I see right away that in my first column, I have positive and negative x, and there's no other coefficient. So I think it would be pretty easy to try to eliminate our x's. So the first thing I'm going to do is I'm going to add equation 1 and equation 2 together, because when I add x and negative x, it should cancel out my x's. So here's what I mean by like how I would write myself notes. This to me says add equation 1 and 2. So I have x plus y minus 2z equals 3. Also, I always put a line through my z because it looks like a 2 if you don't, and I don't want to accidentally add a 2 where I was supposed to have a z, and then all my work will be for nothing, and it's just really depressing. So I try to put a line through my z so I don't mistake it for a 2. Well, I was hoping my x's would cancel out, which they did, but I also didn't notice that my y's are going to cancel out. If anything, that really helped me. It's going to shorten the amount of work I have to do, because now when I add straight down, I'm just left with 1z equals 2. So I literally already solved for z in that first step. But now I'm going to repeat the same idea I had, which was to eliminate my x's, and I'm going to do this in equation 2 and 3, because I noticed earlier that my x in equation 2 was -1 for a coefficient, and my x for equation 3 had a coefficient of +1. So if I add these equations together, my x's should also cancel out. This time my y's do not cancel out, so I'm left with 1y plus 4z equals 11. But I do know what z is, right? Z is equal to 2. So I'm going to plug that into this new equation I found. So now I have y plus 4 times 2 should equal 11. Or I have y plus 8 equals 11. I subtract the 8, I get y equals 3. So now I know my value for z, I know my value for y, and I want to substitute that into one of my original equations to figure out x. And my top equation here is x plus y minus 2z equals 3. I'm going to plug it into here. So I have x plus y, which is 3, minus 2 times z, which is 2, and this should equal 3. I'm going to solve for x. I have x plus 3 minus 4 equals 3. That's x minus 1 equals 3. Add 1 to the other side, and we get x equals 4. Now remember, solutions to these problems are not written the way I have them boxed right now, but you should write that the solution is the point 4, 3, 2. X, Y, Z. And I do recommend checking your work. It's going to take a little bit of time, but you never know if you messed up. Now all you have to do is plug it back in. So you would just check if all of these were true. So x is 4. So is 4 plus 3 minus 2 times 2 equal to 3? Well, it's a 7 minus 4. That does equal 3. Is -4 minus 3 plus 3 times 2 equal to -1? That's -7 plus 6. That does equal -1. And then lastly, 4 plus 2 times 3 plus 2. Does that equal 12? That's 4 plus 6 is 10 plus 2 does equal 12. So after you do that, you feel pretty confident, right? Then you should probably box your answer. Exercise 2, let's solve another system. The last problem was actually pretty nice because we got the answer for one of our variables right away. Sometimes that doesn't happen. In fact, I would say most of the time that doesn't happen. Usually you'll get a system where you end up with, two equations that maybe have both x and y, and then you use the methods from section 1. It just takes a little bit more time, but not always. Exercise 2 is also kind of a unique one, so let's look at this. If I label these problems again, so equation 1, equation 2, equation 3, I see that equation 3 already only has two variables. So it might be a good idea to come up with another equation that only has two variables. And I want it to have the same two variables that equation 3 has. So is there a way that I can, play with equation 1 and 2 to eliminate x and come up with a fourth equation that only uses y and z? I think I can do that if I multiply the first equation by -2, and then I add it to equation 2. Because if I multiply this by -2, when I add that to +2, the x's will go away. So I'm going to start by multiplying that top equation by -2, and make sure you do it to both sides. So that's -2x minus 4y plus 2z equals -4. And I want to add that to equation 2, which is 2x minus y plus z equals 2. Well, just like I wanted, the x's go away. And I'm left with -5y plus 3z equals -2. Okay, I'm going to call this equation 4. Now what I'm going to do is I'm going to add equation 3 and 4. And the reason I want to do that is because I noticed that I have a positive 5y and a negative 5y, so I know those will at least get eliminated. So I have 5y minus 3z equals 2 plus -5y plus 3z equals -2. Well, actually, maybe some of you noticed this. All of it's kind of going to cancel, right? So this is going to add to 0, add to 0, add to 0, and I get back 0 equals 0. And if you remember from section 1, when this happens, where everything goes away and you're left with this true statement, that implies that you have infinitely many solutions. And when we were writing down how to solve these systems, we said that if you get back infinitely many solutions in this smaller system that you created, then you want to solve one of your variables in terms of the other. What that means is I'm going to take one of my equations. So let's just take equation 3, which is 5y minus 3z equals 2. I'm going to solve this for y so that y is in terms of z. So basically add 3z to the other side and divide by 5. So y is equal to 3/5 z plus 2/5. So if I already had my solution, which we're not there yet, but just to kind of give you kind of a heads up of what's coming. For our solution, we're going to have an ordered triple. We're going to have an x, we're going to have a y, and we're going to have a z. I'm solving for everything in terms of z, so my z coordinate is just going to be itself, which is z. And I just found my y coordinate in terms of z. Now I want to find my x coordinate in terms of z. And then what this ordered triple is going to tell us is if I can plug in any z value I want, and when I plug it into what I have for my y, and when I plug it in for what I have for my x, it'll tell me the other parts of my ordered triple that will satisfy this system based off what I pick for z. So everything is going to depend on the value I pick for z, and then I can plug that in here to figure out what my y value would need to be, or plug that in here to figure out what my x value would need to be, right, for some coordinate that satisfies this system. So now let's find our x coordinate so we can finish that solution. So go pick one of your original equations, maybe equation 1, and we're going to solve for x. So I have x plus 2y minus z equals 2. But I know y. Y is what I have over here in blue. So this is really x plus 2 times 3/5 z plus 2/5 minus z equals 2. And if I solve for x, I will then have x in terms of z. So distribute that 2. Adding these z's together, 6/5 z minus 1z is the same as negative 5 over 5z, right? If I get a common denominator here. So 6 minus 5 is going to leave 1. So I end up with 1/5 z. And I'm going to subtract this 4/5 over to the other side. And if I want to add these together, I'm going to need a common denominator, so I'm going to multiply by 5. So I'm really doing 10/5 minus 4/5, which is 6/5. So now moving that 1/5 z to the other side, I get x equals negative 1/5 z plus 6 over 5. And now I have my solution in terms of one of my variables that will give me back all of the ordered triples that actually will satisfy this equation. Because remember, there's infinitely many solutions, right? So if I can figure out my z value, I can plug that in to figure out what my x and y value would need to be. Like I said, exercise 2 is a bit of a tricky one. It looks a little bit weird. Most of the ones we're going to encounter will have actual numbers for our answers, like we did in problem 1, and then you can check your answer. But this is what you would do in the case where you have infinitely many solutions. If you got to this step we have in green and it was something false, you would just be done because you would have no solution, so you wouldn't have to do the rest of these steps. Exercise 3. 1,000 tickets were sold for a total of $15,500. The prices of the tickets were $10 for children, $15 for students, and $20 for adults. There were 200 more student tickets sold than adult tickets. Find the number of each type of ticket sold. This exercise can be solved by setting up a system of linear equations in 3 variables, where the 3 variables are the number of children's tickets, the number of student tickets, and the number of adult tickets. So I'm going to let C be the number of children's tickets, A, or S, be the number of student tickets, and A be the number of adult tickets. So take a second on your own to just try to come up with the 3 equations that would make up our system, given the information in this word problem. And give yourself a few minutes to maybe be confused or not know where to start. Don't just speed forward 5 seconds to find my answer. Like, actually give yourself some time to think and try, and then you can just come back and check if you set it up correctly. You don't have to solve it yet, but let's just set it up together. So pause the video and then come back and check your work. And you should end up with these 3 equations. So let's go through how I got them. The top equation, C plus S plus A equals 1,000, is because it said there were 1,000 tickets sold. And I know the 3 types of tickets I'm selling are children's tickets, student tickets, and adult tickets. So if I add up the number of children's tickets plus the number of students' tickets plus the number of adult tickets, it should equal the total 1,000 tickets. The second equation is kind of the same setup as what we used for our objective function in our linear programming problem with the fuel oil and the gasoline, which is that if you multiply the price times the number of tickets sold, that will tell you how much money you gained from selling that type of ticket. So $10 times the number of children's tickets will figure out how much revenue was gained from selling those tickets. And similarly, $15 times the number of students' tickets will tell me how much money was gained from selling students' tickets. And $20 times the number of adult tickets will figure out how much money was earned from selling adult tickets. And then if you add all of those amounts together, that will give you the total amount of money that was collected from selling the tickets. The last one might be where a few of you maybe made an error, but it said there were 200 more student tickets sold than adult tickets. So I first need to know how many adult tickets there were. If I add 200 to that value, that'll tell me how many student tickets were sold, because the student tickets should be 200 greater than the adult. So you don't want to add 200 to the student, you want to add 200 to the adult, and that'll tell you how many student tickets you sold. Okay, hopefully you did all right. If not, hopefully this made sense and you were able to correct whatever you may have made a mistake on. Now I want you to pause the video again and try to solve the system. When you're done, come back and check your work. And again, don't just jump forward a few seconds. Actually try it. You know, you don't want to try it for the first time when you take a test. You want to try it now so you can practice it. And then if you need help, you can always, contact me and we can go over it some more. So give yourself some time to actually try it, pause the video, and then come back and check your work. Okay, and I ended up with A equals 300, S equals 500, and C equals 200. Or in other words, there were 300 adult tickets, 500 student tickets, and 200 children's tickets. Now, you may have done your work different than me, and that's okay if you got the same answer. You may not have taken the exact same approach as I did. If you got this answer, great. I would just say you're good and you can move on to go into your homework. But if you didn't get that answer, I'm going to walk through the work I did. So, the first thing I did was I looked at equation 1 and equation 2, and I noticed that I could easily eliminate any of my variables because all of the coefficients in equation 1 were positive 1. Looking at equation 3, I saw that the only variables I had were S and A. So I thought it would be smart to eliminate C so that I would end up with another equation only involving S and A. So what I did was I multiplied equation 1 by negative 10. That way when I add it to equation 2, the C's will cancel out. So that's what I did here. I multiplied by negative 10. And then I ended up with negative 10c minus 10s minus 10a equals negative 10,000. And I added equation 2 to this. The c's canceled, and I was left with 5s plus 10a equals 5,500. Then looking at equation 3, I can use the substitution method because I already know what s is. It's a plus 200, and I can substitute that in for s in this new kind of like equation 4 that I found. So where I had s, I replaced that with a plus 200, and then I distributed and solved for a. That's where I got a equals 300. Now that I know a, I can go back in and plug that into equation 3 and solve for s, which is how I got s equals 500. And then I took a and s and plugged them into equation 1, just leaving me with a c to solve for, which is where I got the 200.